Okay, here we go. We're going to do limits at infinity. And for seniors, this means this is your last high school math lesson ever, which may be a happy thing or sad thing. All right, so we are going to be doing these problems on Delta Math, and we're going to see them graphically first. And we're going to notice that in this make-believe graph, it looks like we've got a horizontal asymptote here, right, at y equals 5, and here at y equals 2. Now remember with horizontal asymptotes, it's okay for the function in the middle to cross through them. Horizontal asymptotes just exist to talk about our end behavior. And so anyway, so we would write there are a total of two horizontal asymptotes. Let's see, there is and we write horizontal asymptotes at y equal, there's one at y equals 5. And then there is a horizontal asymptote at y equals 2. All right, now, we haven't used calculus yet. But now let's talk about what does it mean to actually have a horizontal asymptote. So I want you to look at this right here. Now, the numbers, the 4, that's not really what we're looking at. We're looking at 5, so I can change that to a 5 and change that to a 5. Okay. So when we're looking at this end behavior of the graph is going, it's going, it's going, and we know it's never going to cross over 5. It's never going to touch 5, much less cross over it. And so what are we describing? We're describing what's going on with the graph as x is approaching what? X is approaching negative infinity. So let's look at this. The limit as x approaches negative infinity, so the limit of the function as x approaches negative infinity equals 5. That's exactly the calculus behind it. So we would click that one. I would write it like this, limit of f of x as x approaches negative infinity equals 5. And then to describe this part right here, this part of the graph, right, what's going on here? Well, as x approaches positive infinity, right, our graph is approaching 2. It's never going to, so we're going to say the limit of the function as x is approaching positive infinity is 2. So it's an interesting way of looking at our horizontal asymptotes through the lens of calculus. All right, let's do another one. All right, so here we see a couple things, right? We see that we've got a horizontal asymptote, it looks like, right, at x equals -1. So let's write that down. I'm sorry, y equals -1. So let's just write that part down. There's a horizontal at y equal -1. There also looks to be a horizontal right here, right? And that's at, so there's another horizontal at y equals 5, right? And we'll come back and fill in the calculus. But then we also see that we've got a vertical, and it looks like the vertical is right there, right? Looks like the vertical asymptote is at x equals 4. So we've got a vertical at x equals 4. All right, so let's come back and let's do the calculus behind these horizontal asymptotes first. So with the horizontal asymptote, what we're really saying is, as you find the limit of this function as x is heading to negative infinity. And the graph, when we look at the graph, right, the graph's humming along, it's humming along, but it is never, my line is kind of on top of it though, isn't it? It's never going to hit -1. So the limit of the function as x is approaching negative infinity is -1 because it will never touch it, but that's where it's heading, right? It's all about the journey. It is journeying on, but it will never, it's journeying towards -1, but it will never hit it. And then when we look at this second part where we have a horizontal line here, we're really looking at what's going on with the graph as x is heading out to positive infinity. And we see, let's write it, the limit of this function as x is approaching positive infinity, we can see that it's journeying towards 5, but that's its limit, right? It's not going to hit 5. It's not going to cross through 5. And so let's go ahead. Let's get rid of all of these things here so we can just then focus on the vertical. So with the vertical, here's our vertical right here, right? So what's happening here? This is really just looking at the limit, and it's both sides when you look at it. On the left side, as x is heading to 4, what's the graph doing? It is shooting up to positive infinity on the left, and it is doing the same thing on the right. It's just not as close on the right because they're not really showing it past the grid. So how would we write the vertical? Well, we would say the limit of the function as x is approaching 4, that goes off to infinity, so it does not exist, right? So this problem is kind of comparing and contrasting what's going on with horizontals versus what's going on with vertical. So since the title of this lesson is limits at infinity, what we're really focusing most on are these horizontal limits, our horizontal asymptotes, which are our limits at infinity. Okay, let's keep going and see what else we've got. Oh, it says to stop. So we would stop and do those. If you're at home, you can do those. I definitely am going to have the class stop and do those because we're going to move on to something a little different next. Okay. Now what we're going to see is we're going to see it algebraically. So we don't see the graph, and we are not going to stop and write this graph, right? We know that it's well, we could tell it's a rational, and it has a vertical asymptote. It's got a horizontal asymptote. But let's go ahead and see if we can find what the horizontal asymptote is by doing a little algebra. We're going to be clever with algebra. And what we're going to do is this. We're going to rewrite the limit, and we are going to decide to divide every single term by something. And what's something, do you ask? Well, I'm going to look in the denominator, and I'm going to find the x that's raised to the highest power. Well, this is the only x I see anyways. So we're going to use that. And so what we're going to do is we're going to divide every term by x squared. And we're allowed to do this. As long as we do it to every single term, we are not breaking any rules. So here we go. We're going to do the limit, and we're going to rewrite it. We're going to raise up the numerator a bit, and we're going to divide that by x squared, that by x squared. All right, we're going to rewrite the denominator, and we're going to divide this by x squared and this by x squared. And then we're going to rewrite it. All right, so let's go ahead and rewrite it. That equals, we're still in the limit. Once again, we always, even if we're doing algebra, we want to write the limit stuff so we don't forget we're in a limit problem. And so as we simplify, we're like, okay, that cancels out, right? That cancels out right there. And so we're going to rewrite. So we'll have what? 3 minus 4 over x squared divided by 2 plus 1 over x squared. And so now we're ready. We're ready actually for direct substitution. And so we're just going to plug in infinity. And so we're going to do, remember how we talked about this? We can do the limit of each one of these separately. The limit of each one separately. We're allowed to do that. And so as we do that, we're going to say, all right, the limit of 3 as x approaches infinity is 3, because that's the line y equals 3. It's going to 3 no matter where you look. It's going to 3. And when we look at this, if we plug infinity in, like let's go ahead, you know what, let's plug infinity in so we can talk about it a little more. And then the limit of 2 in the denominator as x going to infinity is 2. And let's go ahead and put the infinity down here. It doesn't matter that it's infinity squared in both cases, no. Infinity squared is just infinity. All right, so let's think about what this means. 3 means 3. If I have 4 pizzas and I'm dividing it by an infinite amount of slices, how big are those slices going to be? That's right, 0. It's going to be approaching 0, right? And same thing here, we've got a 2. Our limit, we're still, I'm so sorry, we're still in a limit, so let's get that back. We're taking a limit still here. Okay, well, no, I was right. Undo. I was right. We already did do the limit part. All right, so then 2 is 2, And then one pizza divided by an infinite amount of slices is going to be, right, 0. And so we end up with our limit being 3/2. So what does this mean? Let's tie it all in together. We're finding the limit as x is going to infinity. So we were thinking about a graph. We're really looking at, and I don't know what the graph looks like, but right, it's doing something as it's going to infinity. Oh, that was a good, that was nice, Miss Overby, because really that does look like 3/2. And so this is saying that as x is going to infinity, we actually have a horizontal asymptote at 3/2, right? So I want you to remember, we did this in the Polly and Rats unit, right? We didn't use calculus, though, did we? We just looked at the rational and we said, oh, the rule is if the highest power in the numerator is the same as the highest power in the denominator, then the ratio of the leading coefficients is our horizontal asymptote. So we just memorized that rule because we didn't know calculus then, but now that we know calculus, we know where it came from. We know how to do it without memorizing the rule, which is pretty cool. All right, let's do another one. Let's see. So we're going to do the same thing, right? We're in a limit problem, and we're going to divide everything by x cubed. So we're going to do 3 divided by x cubed minus 2x divided by x cubed over 3. You see what I'm doing. I don't need to talk through this, do I? All right, so it's the same idea, right, that we're going to simplify, and when we simplify, what does that look like? We're going to have 3 over x squared, 3 over x cubed minus 2 over x squared over 3 minus 1 over x cubed. Okay, and when we do this, we see that this 3 pizzas divided by infinity, that goes to 0, that goes to 0. All right, so we're going to have 0 in the numerator, and in the denominator, we're going to have 3 minus 0. So what's 0 over 3 minus 0? It's 0. That means we'll have a horizontal asymptote at y equals 0. And that makes sense, right? Remember our bookshelf thing? Where if our bookshelf were bottom heavy, it's not going to topple over and break. It's going to stay on the floor at y equals 0. Now we know the calculus behind it. So now, guess what? This is going to be our top-heavy bookshelf. We know what's going to happen to the top-heavy bookshelf, right? Let's do the calculus behind it, though. Let's divide everybody by that x. So, All right, and then we're going to simplify. All right, and then when we start plugging infinity in, what are we going to get? We're going to get a 0 here, right? But when we plug infinity here, -2 times infinity is negative infinity, right? We don't need to say the 2 infinity. And then we've got over 3 minus 0. So we're going to get infinity, and when we get infinity, we say the limit does not exist. And that makes sense, because a horizontal asymptote does not exist when a rational function is top heavy. That bookshelf, top heavy bookshelf, which is going to topple over, no bookshelf anymore. All right, so I just want us to know, now we know the calculus behind those rules. Delta math is going to make things look a little more complicated. So let's talk through that. What does it look like with delta math? So we're looking for the highest power in the numerator, all right? So here, it's pretty basic. We see the highest power in the numerator is, in the denominator is x squared. So we would divide everybody by x squared. We also will note, okay, it's backwards. They don't do the exponents in descending order, but that's okay. We can do this problem. We can divide everybody by x squared and be done. This, they're getting a little bit tricky, right? Because this, we're like, what's the highest power? Well, we could, and I'll do it just for one time, we could go ahead and say this times this is 28x cubed, right? And this times this is minus 7x to the 5th, and this times this is 20, and this times this is negative 5x squared. And we'd say, okay, what's our highest power? Our highest power is that x to the 5th, right? And that's what we would divide everybody by. We're not going to do it that way. We're going to get clever, and we're going to be doing some shortcuts. So let's do a shortcut here. Otherwise, we're going to be doing so much algebra and very little calculus. So we don't want to do that. We want to do the shortcuts. So here's what we're going to do. We're going to look and we're going to see that this times this is going to give me my highest power down here. Oops, let me put that down a little bit so we can, okay. So that's going to be, in my denominator, I'm going to get a negative 7x to the 5th, right? And then in the numerator, my highest is going to be this times this. So I'll get an 8x to the 5th. All right, looking at this, do we really have to know the rest of the problem up here and the rest of the problem down here? We do not. We do not, because we know that the highest power in the numerator is exactly the same as the highest power in the denominator. And then we know that technically we could divide everybody by x to the 5th, but we know that when the numerators and the numerator's highest power is the same as the denominator's highest power, then our horizontal asymptote is here, which our horizontal asymptote is exactly the same as the limit as x approaches infinity. So you're just going to put negative 8/7 on the delta math, and I apologize for why they try to make it so difficult looking. You're going to really enjoy the graphing part. I think that really brings home the lesson, the calculus part. All right, we're going to do the same thing here. What's the biggest thing that comes out of here? This times this is going to give me what? Negative 72x to the 3rd. And what's the highest that's going to come out of here? This times this, right, is going to give me 35x cubed. Okay, so if we have, once again, if we did it in descending order, we'd have negative 72x cubed plus da 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 da. And on the bottom, we'd have 35x cubed plus da 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 da. We don't really care. We notice that these two are the same, and so our horizontal asymptote is going to be the negative 72 over 35. Strange answer. I may have done some math wrong. If I have, forgive me. But that would be our horizontal asymptote. And basically, the reason why we're using our shortcut rules is this part of delta math is saying, hey, limit of the function as x approaches infinity, I'm really looking for that horizontal asymptote. The way they've set them up is so much harder than the ones we just did that we have to use the shortcut. And I'm okay with it. I am okay with the shortcut. All right, so let's look at this last one. What's the biggest thing we can find here? That's going to give us what? Negative 15x to the 6th. Biggest thing down here is going to be 15x to the 6th, the same. These are the same. And so therefore, our horizontal asymptote is going to be at negative 15. And that is our limit as x approaches infinity. So hopefully those shortcuts made sense. We can practice those in class if they didn't. But yeah, that's what we kind of have to do with delta math. All right, I think, well, we've got a mini practice. And then after that, we've got delta math day 5 homework. It's our last official homework before we get ready for the test. Thank you for joining me and have a great summer.